In this video, we're going to be looking at the electric field. Specifically, we want to be able to draw electric field diagrams and, of course, understand what the electric field is and then calculate a value for that. Specifically for point charges, which is the simplest method. We'll look at some more complicated methods later. This is basically so we can predict what will happen if you were to place another charged particle in that space. So we have some analogies that will hopefully help us understand the way this works. We know that the gravitational field, or little g, is in the same direction as the gravitational force, and is basically the number of newtons per kilogram that would occur or of newtons of force per kilogram that would, and any mass would feel at that point. Now, that's not exactly how we've usually thought about little g, but we have talked about this a little bit. Normally, we thought about it as the acceleration due to gravity. But that is only true because the acceleration due to anything is the net force divided by the mass. And so we have that relationship here. We know that the mass of the Earth creates a gravitational field such that at any point, a certain distance from the center of the Earth, you'll experience the same acceleration. And so if you're at some point P, 2 Earth radii from the center of the Earth, right, you'll get a quarter of the, little g that we experience on the Earth. So 2.5 newtons per kilogram if placed at P. So if you placed a 1 kilogram mass there, it would feel a weight force or a force of gravity of 2.5 newtons. So if 1 kilogram's there, 2.5 newtons down. 2 kilograms, 5 newtons down. 10 kilograms, 25 newtons down, and so on. So this little g is a property of a point in space. This doesn't care about what mass you place there. It tells you what would happen regardless of the mass. And that actually makes it really powerful, right? Knowing little g allowed us to solve all sorts of problems even before we had much of an understanding of how gravity behaved. Just the fact that we knew that on the surface of the Earth, which happens to be 1 Earth radius from the center, we had an essentially constant little g gravitational field acceleration due to gravity. And so what we want to do is we want to take this idea about a constant gravitational field or gravitational acceleration and connect it to what we now know about the electric force, which we know behaves a little bit like the gravitational force. So if you imagine a single charged particle, this is positive. Generally, you'll see red and red family of colors used to indicate positive charges if we're using color coding, and blue family of colors used for negative, just visually. That's often how you see it. But the electric field is defined in the same way as the gravitational field. It is the electric force divided by the fundamental unit of electricity. In gravitation, it was divided by a kilogram, or mass in kilograms, and in this case, it's divided by charge in coulombs. So it is the electric force, or in newtons per coulomb. It gets a capital E. It's either bold or with a vector symbol over it, because it is indeed a vector. Notice we have a vector divided by a scalar, giving us a vector. So this electric field, capital E, is a property of that point in space, created by whatever charge happens to be nearby. If you think of a point P, some distance away, it might have 200 newtons per coulomb as its electric field due to this positive charge. If we put charges there, what forces act on them? Well, if we put a positive 2 coulomb charge there, then we would multiply that by the 200 newtons per coulomb electric field to get 400 newtons. And since it's a positive 2 coulomb charge, it would be repelled, so it would feel a force straight up in our picture. For a negative 0.1 coulomb charge, we would feel a 20 Newton force that is attractive down toward positive Q. And if we had positive Q be an electron, that would be 1.6 times 10 to the negative 19 coulombs. Multiply that by 200 newtons per coulomb, and we get 3.2 times 10 to the negative 17 newtons. And again, repulsive because, this is a proton, right? A positive elementary charge would be repulsive. Okay, so this is how it behaves, just like the gravitational field. Now, another way to think about this is that instead of just calculating it for one point in space, we want to think about it sort of everywhere. So what we do is we imagine a tiny test charge, and oftentimes we imagine sort of the point of a pencil, right? If you imagine there's the tiniest little bit of test charge, Q naught, so small that it's it's even smaller than an elementary charge, even though we know we can't do that. And we're only bringing it around to check what is the field over here by my ear, by my forehead, everywhere around in space, right? And you check and you probe the field is the language we use. And we see what would happen to this positive test charge at that point, and we use that to help us draw the electric field. Well, if you have a big positive charge somewhere, then the closer you get to it, the bigger the the electric force would be, and the more repulsive. And the further out, the weaker it gets. And so by convention, the electric field always points in the direction that this tiny positive test charge would feel a force. And so what does that mean for us? Well, what it means is if you take a positive charge, as you see up here, the little yellow positive charge with some blue lines coming out of it, the electric field exists everywhere in three-dimensional space. This is just a 2D representation, but field lines should be coming out of the screen at you and going back that way. It's spherically symmetric. And so the electric field exists even when there's no test charge there to feel it. It's a property of a point in space, and we can check it by going in and probing the field, or we could place another charge there and see what force it would experience, but it's always there everywhere in space. And these electric field arrows always show the direction that a force would act on a positive test charge. This is just convention. We mostly have Benjamin Franklin to blame for that, because we didn't realize that positive charges didn't really do much moving because they're locked in nuclei, because we didn't know what was going on inside the nucleus at the time. C'est la vie. A couple of other things that are helpful to know about this, at least interpreting this diagram, right? When the lines get further apart, the further out you get. That's a weaker electric field. The closer packed they are, a stronger field. So it's sort of a visual language for understanding this. The electric field lines always start on a positive charge and they end on negative charges, or way out in infinity if you only have one charge like this. The field lines never really stop in space. So that's why you see these sort of arrow continuous lines showing that they go on to infinity. The diagram just stopped because we ran out of space. The electric field has only one value and direction at a given point, right? If you have electric field from multiple sources, we sum them up and figure out what the electric field at that point is due to everything. But there's no such thing as multiple electric fields at a single point. So what do we do? When we talk about drawing electric fields, I want to show you a few different examples of what this might look like. When I say monopole, that means a single charge. When I talk about a shell, that means something where the charge is spread out evenly on the outside of a sphere. A dipole has two charges. They could either be the same or different charges, like opposite or negative. And then we can look at what happens when like charges are next to each other. And then oppositely charged plates. So this is two flat things brought near each other. Those are important for understanding of electricity. We'll look at that later. And then what happens if you could actually imagine an infinitely large sheet or plate of charge? All of these will be interesting for helping us understand electric field. So we start with a monopole. We've already looked at a positive monopole, and the electric field lines kind of went outward. That was our example. But here, they're pointing inward, because if you remember taking our positive test charge and placing that everywhere in space, if it were a positive charge, it would always feel pulled toward this negative. The closer you get, the stronger the field, and that's borne out by the fact that as you go in closer and closer, the electric field lines get closer together. You get basically the same pattern if it's negative charge on a sphere. The only difference is inside, there's no electric field because there's no electric force on a charged particle in there because of the shell theorems. So outside, it looks just like a single negative charge, but on the inside, it's zero electric field. A dipole, a positive and a negative charge, makes this pattern that you've probably seen something similar to if you've ever played with a magnet and iron filings. Magnetic field behaves somewhat differently, but there are some similarities, right? You notice that the densest field lines are nearest to the charges, and right in the middle there, they're very dense as you go between the two charges. The electric field that we get here is actually the sum of those two radially symmetric electric field sets from each of these monopoles added up at every point in space. The kind of math of that is, I won't say it's difficult, but I also won't say it's simple. You can figure it out relatively easily, at least along the central axis there, right through them, or vertically, using a relatively simple set of algebraic equations. But if you wanted to map it for everywhere in space, you would need to have x and y components of the electric field added up everywhere, or at least in a big, relatively small grid. So that's like a calculus problem, and we'll look at that in a little bit. If the charges are the same, like say two positive charges, you get an interesting result, right? In the middle, if you imagine, they are both providing an electric field directly opposite each other. So there's a region where the electric field adds up to 0, and it sort of makes this interesting kind of repulsive area. So there's this kind of area in the middle. There's very little, certainly right in the middle, there's no electric field. And then it's pretty weak until you get out of that middle section. And if you go along that vertical line, it's actually 0 everywhere along that line, which is kind of interesting. If you have two oppositely charged plates, pieces of metal, this is what, if you've ever heard of a capacitor, is basically a capacitor. You have a positive side and a negative side, and they're separated by an insulator. It could just be air, it could be something else, and we'll talk more about how capacitors behave later. But you get these electric field lines that are essentially parallel. As long as the plates are relatively close together and relatively large, there is some curving around the outside at the edges, but near the middle, you get these nice parallel, uniform electric field lines. Because the fact that they're not getting further apart or closer together means the strength is the same. More on those dotted red lines later, but they have to do with potential and potential energy. And outside the plates, you essentially get 0 electric field. We can show ourselves why this would be the case with a simulation and example in a little bit, but that's the basic idea. The other example is an infinitely long charged plate. And this will give you uniform electric field lines going in both directions. Now, of course, it's very hard to make an infinite plate, but it is not hard to charge up something relatively big, like the size of your desk or a table, uniformly, and then get pretty close to it. And the closer you are to something, the harder it is to sort of see the edges. And if you imagine, taking my test charge and bringing it down until it's very close to the table, probably can't even see that. If you were to shrink yourself down and be that person, you wouldn't really necessarily even be able to tell where the table ended. So you would get this effect that is essentially a uniform electric field. So this says discuss with your neighbor, and this is kind of how we're going to start when we come back into class on Monday. How do you know the direction of the electric field? How do you tell from the electric field diagram if the field is uniform or not uniform? And how do you know the direction of the force on a charged particle in an electric field? These are kind of the fundamental things that we need to know about electric fields. Okay, so let's jump and do this. If you have a point charge, a shell, or a sphere, anything that is spherically symmetrical, we know that for all electric fields, the electric force that a charged particle, a test charge, would feel divided by that charge will give us the electric field. And so if we use the electric force equation for two charged particles, and this is why it only works for point particles or shells or spheres, because you need to be able to use this equation. Then you divide out the test charge, you end up with this. The electric field due to a single charge float somewhere in empty space is kq over r squared, right? It's just the amount of force per unit charge. Now, I can't stress this enough. This only works for a point charge or shell or sphere, something that acts like a point charge, the electric field due to it. And now you can do this for multiple point charges, right? If you have maybe half a dozen, it's relatively easy to find this effect at another point in space from each of them and add them all up as vectors. But the more you get, the more complicated it is. And if the shape is not spherically symmetrical, it becomes complicated fast. And so we need another method, which we'll learn in a little bit. So what we can do is we can add up the effect of lots of individual charges. The rule of superposition, as we learned for forces, applies to these vectors as well, the electric field vectors. Okay, so here's an example of how we might do this. We have charges 1 and 2, and we have this point in space midway between them. We want to know what the electric field strength is. Now, these are both positively charged particles. And we start by making sure we understand, is there a charge at point P? No. We are going to take our test charge, sort of in our own mind's eye, and think about placing it there and saying, what would happen if I placed a point charge there? Then we'll take it away and say, okay, what's the electric field at that point? We know, since these are point charges, we can find the electric field due to the first one, K, Q1 over R1 squared. That's the distance to the center, a half a meter. And we get 1.44 times 10 to the fifth newtons per coulomb to the right. Right? It would, if there were a positive charge there, it would feel pushed away from Q1. We can do the same thing for the electric field due to charge 2, and it has an electric field to the left. It's a smaller magnitude, only 10 to the fourth, because it's a smaller amount of charge, only 1 microcoulomb. You're going to see that a lot. A coulomb ends up being a really big amount of charge, so we use micro and nanocoulombs a lot. Then we can add those two up as vectors, and we had a 1.08 times 10 to the fifth newtons per coulomb to the right. So we can go a little bit further and say, all right, well, what if this is the net force, the net electric field at that point, or more importantly, that is the electric field at that point. How much force would an electron feel if we placed it there, and in which direction? Well, the elementary charge is 1.6 times 10 to the negative 19 coulombs. Multiply it by that electric field we found at point P, and it will experience 1.7 times 10 to the negative 14 newtons. And it will be to the left. Why? Because the electric field shows the direction that a positive charge would feel a force, and an electron, of course, is a negative charge, right? The other thing we might ask ourselves is, what is the acceleration of that electron if we release it, the instant we release it? Well, that's just a Newton's second law equation and relationship. Net force divided by the mass gives us 1.87 times 10 to the 16 meters per second squared to the left. The acceleration always has to be in the direction of the net force. Can we talk about this in terms of kinematics equations? No. Acceleration is going to change because the electric field is going to change, which means the electric force is going to change as you move toward Q, right? This is not a uniform electric field here. When can we use them? Right, as I mentioned, only if the field is uniform. And a uniform electric field looks like this, a bunch of parallel lines. So why do we actually care about the electric field? As I've said, it is like the gravitational acceleration or gravitational field, in that you can predict what any charged particle would do at that point if they were there, instead of having to recalculate things for every individual charge. And because of this, it is a powerful way of thinking about the effect of electric or charged particles in a region of space. So I am going to have you play with this in class tomorrow when we all get together, the charges and fields simulation. But I also want to kind of give you a quick tutorial of how it works and how we learn, what we can learn from it. Here is the PhET University of Colorado interactive simulation on charges and fields. It also does some stuff with voltage and potential, but that's not something we need to worry about right now. So we are going to start with just the basics of what happens if you place a charged particle. Now, I told you earlier in the video that electric fields should be these continuous lines. They shouldn't sort of start and stop. But that's a little bit hard to render on the fly. And so these are basically little arrows that kind of point out what the electric field would be at a given point based on a charge being placed there. So they're an approximation, of course. But what we can see here, hopefully, that will make some sense to us, is that they're all pointing away from the positive charge particle that I placed there. Now, in addition to that, pointing away from that, you notice that they are brighter when they are stronger field, and when they are closer, and they get weaker as they go away. So it's a different way of visualizing the electric field. You can look at just the direction you want if you want, but this is giving you kind of that picture. You may want to turn on a grid so you can kind of see what's happening here. Better see what's happening. There's also an option in this program, if you click on it, to change it to what's called Projector Mode, which does a lighter background. but I'm going to leave that off for now. I'll probably use that in class. You can also, instead of a positive charge, use a negative charge, and you'll get the electric field kind of pointing inward. If I turn off the electric field for a moment and just kind of place this charge in space, and I bring in my electric field sensor, this little dot is not a charged particle, but it is attempting to represent for us that test charge that we talked about, right? As I bring it farther away, the arrow gets smaller. As I bring it closer, the arrow gets bigger. If I swap out the negative for a positive, now it's pointing outward, right? Always radially outward, okay? What we can do then is we can turn the electric field back on to give us a sense of this. We can see what happens if you put a bunch of positive charges together. Notice their effects sort of add up so that as I add more of them, we're kind of getting a relatively uniform, more parallel field in the middle. And in fact, if you pack this in a nice straight line, which is one of the things that you'll be looking at with regards to the electric field, you actually can kind of simulate that. You can also put on some negative charges. And if you put enough of them there, you can get an interesting effect. I'm going to reset this for a moment, electric field and grid, and we'll just do a dipole because that is a relatively simple thing to look at. And so there you get the nice positive to negative. You're able to kind of do some measurements here. If you want to know how far apart things are, you can take your electric field sensor and see that, right, the strongest electric field is there, but it stays pretty strong in the middle here, and it's basically always to the right, which is kind of interesting. Here it's inward, here it's outward, right? So you can kind of explore that. So that's the end of our look at electric field today, specifically for individual point charges or a few point charges. We are going to look at a more complicated, well, just a little bit more of a thorough, but definitely more complicated to think about method if we have distributed charge in, say, rings or arcs or discs or a flat plate and that kind of thing next time.